Hello everyone, welcome to my class. Today we will talk about Heisenberg's uncertainty principle. Heisenberg's uncertainty principle was given by Werner Heisenberg and he was a German physicist. In 1924, he simply stated that when the position and the momentum of a body is measured simultaneously, the product of the uncertainties in measurement must be greater than the ratio of the Planck's constant to 4 of pi. That is, it is not possible to measure simultaneously the position and momentum of a microscopic particle with absolute accuracy or certainty. The same thing can also be defined as the product of uncertainty in position and uncertainty in momentum of a microscopic particle is always constant and is equal to or greater than h upon 4 pi. Now, if delta x is very small, that is, the position of the microscopic particle can be measured accurately, then delta p will be very large, which means that momentum or the velocity of the particle cannot be measured with great accuracy. Similarly, if delta p is very small, delta p means momentum is small. That means we can measure the momentum or the velocity accurately, but then uncertainty in measuring the position will be maximum. But if delta x is 0, then the position can be located with absolute accuracy, but delta p will be infinity. That means momentum of the microscopic particle cannot be measured at all. So, for solving problems, this equation can be rewritten as delta x into delta p is equal to h upon 4 pi. Now let us apply Heisenberg's uncertainty principle to an electron in an orbit of an atom with h 6.626 10 to the power minus 34 joule second and m, that is mass of electron, 9.11 10 to the power minus 31 kilogram. If we substitute these values in delta x into delta v is equal to h upon 4 pi m, then we will come to know that delta x into delta v is 10 to the power minus 4 meters square per second. If uncertainty in position is 10 to the power minus 4, then uncertainty in velocity will be 1 meter per second. So Bohr concept of fixed circular path with a definite position and momentum of electron have been replaced by stating that the electron has the probability of having a given position and momentum. Heisenberg's principle applies to only dual-natured microscopic particles, not to macroscopic particles, whose wave nature is very, very small. Now let us explain Heisenberg's uncertainty principle with an example. Electromagnetic radiations and microscopic matter waves exhibit a dual nature of mass upon momentum means and wave character. They have got momentum as well as wave character. The position and velocity or momentum of macroscopic matter waves can be determined accurately simultaneously. For example, the location and speed of a moving car can be determined at the same time with minimum error. But in microscopic particles, it will not be possible to fix the position and measure the velocity or momentum of the particle simultaneously. For a particle of mass 10 raised to the power minus 6 kilogram, we have delta x into delta v is equal to h upon 4 pi m. Put h is equal to 6.626 into 10 to the power minus 34. Put m equals to 10 raised to the power minus 6 kilogram. Then delta x into delta v will comes out to be 0.528 into 10 to the power minus 28 meter square per second. Now this product is extremely small, and for particle of mass greater than 1 microgram, that is 10 to the power minus 6 gram, the product will be still smaller. Hence these values are negligible. Now an electron in an atom has a mass of 9.11 10 to the power minus 31 kilogram, means very small, so not visible with the naked eye. A powerful light may collide with the electron and illuminate it. This illumination helps in identifying and measuring the position of the electron. The collision of the powerful light source while helping in identification increases the momentum of the electron and hence making it move away from the initial position. Thus, when fixing the position, velocity or the momentum of the particle would have changed from the original value. Hence, when the position is exact, errors occurs in the measurement of velocity or momentum. In the same way, measurement of momentum accurately will change the position. Hence, at any point in time, either position or momentum can only be measured accurately, and simultaneously measurement of both of them will have an error in both position and momentum. Now the question arises, why electron cannot exist in the nucleus? Let us consider that we want to place the electron in the nucleus. Then definitely the uncertainty in the position will be the radius or the diameter of the atomic nucleus. So that is of the order of 10 raised to the power minus 15 meter. Now if the electron were to exist within the nucleus, the maximum uncertainty in its position would have been 10 raised to the power minus 15 meters. So taking the mass of electron as 9.1 into 10 to the power minus 31 and substituting these values in the equation, delta x into delta p is equal to h upon 4 pi. And what is delta p? Change in momentum is mass into velocity. So mass into change in velocity. So delta x m delta v is equal to h upon 4 pi, or delta v, that is change in velocity, or better to say uncertainty in velocity, is equal to h upon 4 pi into delta x into m. Substituting all the values, we will get the value of delta v, that is uncertainty in the velocity, and it will come out to be 5.77 into 10 raised to the power 10 meters per second. Now this value is much higher than the velocity of light. Velocity of light is just 3 into 10 to the power 8 meters per second. Hence, an electron cannot exist in the nucleus, because if it is to exist in the nucleus, it has to move with the speed which is much more than the speed of the light, much greater than the speed of the light. Here is a numerical, that is, show that Heisenberg's uncertainty principle is of negligible significance for an object of mass 10 to the power minus 6 kilogram. This numerical we have already done in our explanation. Another numerical, the uncertainty in the position of a moving bullet of mass 10 gram is 10 to the power minus 5 meters. Calculate the uncertainty in the velocity. So one thing is given, that is delta x is given. What we need to calculate is delta v. Using the equation, delta x into delta p is equal to h upon 4 pi. Substituting, delta x into m delta v is equal to h upon 4 pi, and delta x into delta v is equal to h upon 4 pi m. Here we have been given the uncertainty in the position. So for that we need to just calculate delta V using the formula h upon 4 pi m into delta x. Using this formula and substituting the values, we will get the delta V as 5.27 into 10 raised to the power minus 28 meters per second. That's all about Heisenberg's uncertainty principle.